Now that we've seen how imaginary unit can help us solve quadratic equations, we need to discuss further this concept of imaginary numbers and where that's going to take us. So I'm going to go to another sheet here that I've prepared to kind of discuss some of the possible solutions that you've seen in solving quadratics, as more specifically the types of answers that you may have seen while using square roots. So if you look at the first part here, if you look at our first example that I've made up, x equals plus or minus 2. This would be a situation where we took the square root of a number and it led us to a perfect square, and it gave us two real solutions. In this case, those solutions would be real. Then we added the idea of the imaginary unit. So we said, okay, if we end up with a negative square root, we understand that I equals the square root of negative 1. And so in this second example, we end up with plus or minus 2i. And so this would be what we would call two imaginary solutions. And so then we understand that we could have two imaginary solutions and how that affects our graph and our x-intercepts and whether we can factor or not. So we learned a lot of connections there. Then as we move through this, we should recognize that there's actually a third possible way for our final answer to look. In this case, we have the imaginary part of the answer, but then we also have this real number sitting out in front of it, and the real number is actually being added to the imaginary part, which, since those are not like terms, they can't actually be put together. So we have to leave our answer in this form of 3 plus or minus 2i. So we have this situation where we have two solutions because of plus or minus, but we have a real part plus an imaginary part. And so we need to discuss how this fits in the grand scheme of things as far as the way we deal with different numbers. So we'll go back to the notes, and we're going to have a nice little visual of what we're discussing here. So if we look here at this box, we can see that we have real numbers, which we've been dealing with for a while now, and so our answer could end up being just simply real numbers. And of course that could include square roots because those are part of the real number system. Then we also found out that we could have an answer that was just a 2i or plus or minus 2i, and those were an imaginary numbers. And so we can see that when we put just the imaginary part, we have what's called a pure imaginary number. There's only an imaginary part involved in that particular answer. And then lastly, we come up with this part where we can have a real part to the answer and an imaginary part. And this is what we're going to call an imaginary number, but more so we're going to call this a complex number. So you can see that the complex number actually is a result of a real number plus an imaginary number. So when we take a real number and an imaginary number, that's when we're going to get a complex number. Now it's very important that we write these in the proper form, and you can see that a complex number has a standard form where the real part comes first and the imaginary part comes second. So we need to keep that in the proper order whenever we're writing our answers. We also recognize that when we have a pure imaginary number, that the coefficient comes in front of the imaginary unit, just like it would if it were a variable. So we treat the imaginary unit I very much like a variable such as x or y whenever we're working problems and writing it in the proper format. Now, just like x and y, whenever we have an imaginary unit involved in an operation, we can do various mathematical operations like addition and subtraction, multiplication and division. So in this particular video, we're going to discuss those different types of operations that we can use in complex numbers. So let's take a look at a couple of possibilities. You can see here that imaginary numbers can be added and they can be subtracted. What I want you to focus on here is the structure of this problem may look confusing, but really what you need to remember is that this works the same as combining like terms. So if you have two real numbers, you can add the two real numbers together. If you have two numbers with an imaginary unit attached to it, you can add those together just as if it were representing a variable. It just so happens that this particular variable has a defined value that goes with it. So as we look through some of these problems that we're about to work, you'll notice that this is no different than what you did in Algebra 1 or pre-algebra when you were adding x's and y's and things of that nature. So let's take a look at some sample problems that we've got in the notes. If we look at sample problem number 2, we have a couple situations going on. Now, I do not like the way the sample's laid out, so I'm going to give you a different look as to way to write this. If I were working this particular problem, I would simply drop the parentheses. So I would have 4 minus I plus 3 plus 2I. And then I'm looking for the like terms. So I can simply see that the 4 and the 3 are both real numbers, and so I can put those terms together to equal 7. And then secondly, I can see that we have two terms with the imaginary unit in it, and if I take a negative I plus 2I, that's going to give me a positive 1I, or just an I. And so our final answer excuse me, would be 7 plus I. And so this is just a situation where we're combining like terms. Now part B has a situation where we're subtracting two complex numbers from each other. So notice that each of these complex values are written in standard form. But what we have here is we have a negative in front. So this requires a distribution of the negative value before we can actually start to combine like terms. And then the remaining problem would be the same. Now, if you notice, in this particular case, we have a situation where we have a negative 5i and a positive 5i, which created a cancellation of the I values. So we would just have a final answer of 6. And we can continue to use all of the properties that we use with real numbers and variables. So you would want to do that where the I just acts as a variable. So let's take a look at sample problem number 2. What I'd like you to do now is just pause the video and work sample problems A, B, and C using combining like terms, but now we're using complex numbers and the imaginary unit instead of x's and y's. And keep in mind, it wants the final answer in standard form, which means that you need to write your final answer with the real part first and the imaginary part second after you finish combining all your like terms. So go ahead and work these now. Okay, as I told you before, I like to drop the parentheses as soon as I can and then combine like terms from there. So if I look at this problem, I'm going to have negative 1 plus 2i plus 3 plus 3i. If you like to reorder all your like terms and put them together, you're more than welcome to do that. So you have negative 1 plus 3 plus 2i plus 3i. Now you can see we simply have our like terms next to each other, and then you can put those together. And so negative 1 plus 3 is going to give us 2, and 2i plus 3i is going to give us simply 5i. I have the real part first and the imaginary part second. So that is going to represent our complex number written in standard form when we put these two expressions together. Okay? So let's take a look at the sample problem 2. Here, or part B, excuse me. Here we have a negative in front that's going to be required to be distributed first. 2 minus 3i, and now I get negative 3 and a positive 7i. If you can do this in your head, you're more than welcome to. You can combine the like terms. So in this case, I have 2 and negative 3, which is going to result in a negative 1. Then I have negative 3i and a positive 7i, which is going to result into a positive 4i. And this is going to give me my complex number in standard form again. And then finally we have our last one here that just has a couple additional operations in it. So first we have to distribute this negative, so we can take 2i and then negative 3 minus I plus 2 minus 3i, and then we need to combine like terms. So as I'm looking for my real numbers, negative 3, positive 2, it's going to give me a value of negative 1. And now I have an extra imaginary term in here. 2i minus I minus 3i is going to give me negative 2i. And that's written in standard form. And that's how we do addition and subtraction of complex numbers. Now, let's take a look at some other operations that we may run into. You can see in example number 3, we have some multiplication going on here with the imaginary unit in there. And this is going to work just like multiplication in any other with any other variable form. So we're going to, in part A, distribute the monomial to the binomial. Now, this is where the concept of I equaling the square root of 1, negative 1. If I were to square both sides, I would get I squared equals, and of course the square and the square root cancel each other out, so that would be I squared equals negative 1. These are two extremely important definitions of imaginary unit that you need to know and understand. And in this particular set of problems, you're going to see that this second part is actually going to come into play quite often. So if we look at sample A, as we distribute the 5i across the binomial, we actually get a 5i squared just like we would have if we had another variable. But the difference between I squared and say an x squared is that I squared actually has a defined value. I squared is going to equal to negative 1. So we actually need to replace I squared with the negative 1 value and continue our operations. And you see we get negative 10i and a negative 5, and of course we need to rearrange those values so that it's written, the final answer is written in standard form. So now when we multiply, and we're going to be multiplying a pair of imaginary units together, we're going to run into I squared quite often. So you can see here in part B, we're going to end up foiling. And through the foiling process, we get an I squared, and that I squared is going to give us a negative 1, and we can consolidate all that to get our complex number in standard form. Now as you're going through this, you need to pay real close attention to example C. This is probably one of the most important examples in this set of notes. If you look at example C, we have 6 plus 3i times 6 minus 3i. It's kind of like a difference of squares problem, except this is a little different from the standpoint that we have an imaginary unit in here, which is going to create a unique situation. So we have a different sign with the same within the same terms. This is what we call a complex conjugate. And you need to understand the definition of a complex conjugate. And we're going to get into the next video, complex conjugates, in great detail. But this is an extremely important example so that you understand what actually happens with the complex conjugate. If you notice during the foiling process, we have a situation here in the middle where, just like difference of squares, the middle term, or the B term, actually cancels itself out. Negative 18i and a positive 18i actually eliminate each other. And then of course we cannot forget the situation that I squared will turn into a -1. But as we go forward here and we consolidate all of this, notice that our final answer in standard form for complex numbers is simply a real number. Because what happened here is we got a real number plus an imaginary number, but our imaginary number ended up equaling to 0. And so that being the case, we were only left with a real part. So whenever you're dealing with complex conjugates, you need to recognize that that actually eliminates the imaginary unit from the final complex answer. So that is going to be a very important concept in the next video or later on in the section of notes. So recognize complex conjugates when you see them and understand what they can do for you as you're working a problem. So, alright, now that we've taken a look at those 3 examples, we can move on down to sample problem 3. Go ahead and pause the video at this time and take a moment to work these 3 sample problems. Be sure to try to identify the complex conjugates if you see them and try to anticipate what your final answer should look like. So go ahead and work these at this point. Okay, if we look at sample problem 3, part A, we'll go ahead and work through these problems. So we're going to start by distributing the negative I across the 3 plus I. So we're going to get negative 3I minus I squared. Now this is very important that you only replace the I squared. So let's take a look at this. This is another place where using parentheses and substitution is extremely important. So we'll have negative 3I minus, and then of course I squared is going to turn into -1. We'll have negative 3I plus 1. Notice that it said to put the complex number in standard form, so we would need to write that with the real part first, the imaginary part second, and that would give us our complex number in standard form. Okay, very good. Now we'll move into part B. Part B, we have 2 binomials that we have to multiply together, so we'll go back to our foiling process, which requires us to distribute twice. So we're going to take the 2 and distribute it first. So 2 times -6 is -12. Then 2 times -2i is -4i. So the 2 has been distributed. Now we're going to distribute the 3i. So 3i times -6 is -18i. And then lastly, 3i times -2i is -6i squared. We need to combine like terms. So we're going to get -12i minus 22i, and then of course I squared is going to become a -1, and of course we're going to use our parentheses for that, leaving us -12 minus 22i plus 6. This gives us a couple more like terms to put together. So we're going to end up with -6 minus 22i. Since our real portion is first and our imaginary portion is second, we now have our complex number in standard form. Okay, and then our last example, part C. Hopefully you recognize that we had the same term with different signs, so we're dealing with complex conjugates here. And if you recall from the previous example, whenever we have complex conjugates, we should know that the imaginary unit does get eliminated, so our final answer should just be the real portion. So let's see how this works out. So we'll still go through the foiling process. We're going to distribute the 1 twice. 1 times 1 is 1, and 1 times -2i is -2i. Then we need to distribute the 2i part. So 2i times 1 is a positive 2i. And then 2i times -2i is -4i squared. As we combine like terms here, we can clearly see that the -2i and the positive 2i cancel each other out. So we're going to be left with 1 minus 4. And of course we need to replace the I squared with the -1, so that's going to give us 1 plus 4 which simply gives us 5. And this is written in standard form for a complex number, even though it's just the real portion. Okay, very good. Those are complex number operations. So hopefully you should be comfortable doing that, since most of those operations act just like a variable of x or y, with the added portion of I squared equaling to -1. Okay, very good.